All right, we're going to take a look here at number three, or part D of number one, actually. What they want us to do here is, so we've got all the information we had before. They tell us that the pipe can hold 50 feet of water before it overflows. And the water flows in according to those functions that they gave us earlier. I'm just writing R of T D of T. That's the rate that the water comes in, the rate that the water goes out. We want to write an equation involving one or more integrals that gives the time when the pipe will begin to overflow. So we want to figure out when that amount of water in the pipe is equal to 50, okay? And notice that they ask for an equation involving integrals. So think about what's happening here. We've really got three things. How much total water is in the pipe? And if you remember, it started with 30 cubic feet of water, okay? So you've got that initial value, okay? You always want to include that. Second of all, how much water comes in, okay? Well, we can integrate the rate at which water comes in, okay? Big idea of this whole section is if you take the integral of a rate, it tells you how much change occurs because of that rate. So we can take the integral of that rate, okay, from the starting time is 0, right, to the ending time, and we don't know what that time is, okay? So, maybe I could call that variable, W or something like that, the moment when it overflows, okay? So they ask for an integral expression or an integral equation. An equation. So, it might be from 0 to 5 hours. It might be from 0 to 2 hours. We don't know. But this is the water that was already there. This is the water that came in. But remember, water is also constantly leaving at a changing pace. So we have to remove the water that's already left. So we can subtract the integral from 0 to whatever that overflow time is of d of t. Okay? And so we want the amount of water that was there plus the amount of water that's come in minus the amount of water that's left to add up to equal 50. Okay, and we can take a look at their solution here, and we can see they don't actually ask us to solve this. So let's see what they do here. So we can see solutions to these other parts here, and we've kind of talked about most of these. By the way, we already, if we're to this point, we have 7 out of 9, which would have us at a 5 pace. I actually think part D is a little bit quicker than part C, actually, though. So it might be easier to get a 7 by getting A, B, and D. But if you notice here, now they make it one integral. They do an overall rate. We actually did an overall rate earlier. We just said the overall rate of water coming in was the rate that it comes in minus the rate that it leaves. And they just did one big integral of that whole thing. But remember, you can add 2 integrals, or you can combine it as one integral. It's the same thing. Anyway, again, they didn't ask us to solve. Notice they did make a variable here, and actually I guessed a W for water. So remember, you're not subbing in for T here. You're subbing in for the bound. So like you're starting out with 30 cubic feet of water, and then maybe you're going from 0 to hour 6. And that would tell you how much total water is in the pipe after the 6th hour. So how much has come in over 6 hours, and how much is left over 6 hours, plus how much was in there originally. And obviously, if you had the original functions, if there were things that you could integrate, you could possibly try to solve these equations. But these are really complicated calculated questions. So a lot of times when the functions are really complicated, they just are going to ask you for the setup. So good stuff. You're going to see a lot of these themes. The idea that if you integrate a rate, you're integrating a derivative to get back to your original function. And if you integrate that rate over a time period, it tells you how much change occurred over that time period because of that rate. Very much the same thing, just a more general version of what we did with velocity problems. We took an integral of velocity, which was a rate, which was a derivative of position over time. It told us how much displacement occurred. We added that to the initial position. Okay, so these are exactly the same types of problems. Your rate's just not necessarily a velocity, but still very closely related to what we did on the first set of FRQs. So hope that helps.